The three sorting algorithms we have talked about so far are inefficient and run in quadratic time. Over the next few videos, we're going to look at more efficient algorithms with time complexity of n log n. The first one of these is merge sort. The idea of merge sort is to break down a list into smaller and smaller sublists, sort those, and merge them back to build a completely sorted list. Let me show you. We start off by dividing this array into half. We can find the index of the middle element by dividing the length of the array by 2. So 5 divided by 2 is 2. That's the index of the middle item. We split the array into 2 subarrays. In coding terms, that means we're going to allocate 2 smaller arrays and copy the items from the input array into these new arrays. So that's one of the important characteristics of merge sort that you need to be aware of. We're allocating additional space for this algorithm to run. We didn't have to do this before. Now we repeat. Let's focus on the left subarray. Again, we divide this from the middle and we get 2 new subarrays. So we recursively divide an array until we cannot divide it anymore. Now we have 2 single item arrays, and we know that an array with a single item is already sorted. So now we should merge or combine these 2 arrays in a manner that the resulting array is sorted. So between 8 and 2, 2 is smaller, we insert it first, followed by 8. Now we repeat the same steps with the subarray on the right. So we calculate the index of the middle item, that is 3 divided by 2, which equals 1. We cannot divide the array that contains 4 anymore, so we're done here. Now we divide the right subarray. We cannot divide this further, so now we should merge these 2 subarrays. 1 is smaller, so it comes first, followed by 3. Next, we merge the array that contains 4 with this other array. We read the first item from both arrays. Between 1 and 4, we pick 1 because it's smaller. Now we advance our pointer and read the second item of the right array. 3 is smaller than 4, so we pick that next. We have read all the items in the right subarray, so now we add all the items from the left array, in this case, 4. We're almost done. We just need to merge these 2 arrays. Again, we read one item from each array and pick the smaller one. That is 1. Now we advance our pointer and read the next value. Between 2 and 3, we pick 2. Next, between 8 and 3, 3 is smaller, so we take that. Between 8 and 4, we pick 4. And finally, we insert 8. Our array is fully sorted. So merge sort is what we call a divide and conquer algorithm. It works by recursively dividing a problem into smaller subproblems until they become easy enough to solve. Then it combines the solutions to build the solution to the original problem. In part 2 of this series, we had several divide and conquer algorithms. For example, we calculated the height of binary trees by recursively calculating the height of the left and right subtrees. Now let's do complexity analysis. Here we have 2 operations, dividing and merging. Earlier in this series, I told you that whenever we're dealing with problems where we have to recursively divide that problem into half, we have logarithmic time. So if you have an array of n items, the maximum number of times we can divide that array into half is log of n. So dividing runs in O of log n. Then we have to merge these small single item arrays. This will be an O of n operation because we have to read each item from each subarray to build the output. So the time complexity of merge sort is O of n log n. If you look at bigocheatsheet.com, you can see that algorithms with n log n time complexity are way more efficient than algorithms that run in quadratic time. So merge sort is faster than the previous algorithms, but it comes with a cost, the cost of allocating additional space. How much additional space should we allocate? Well, every time we split an array, we have to allocate 2 new subarrays. All these subarrays combined together take the same amount of space as the original array, right? So here we have O of n space. Note that when merging these subarrays, we don't need to create a separate array. We can simply copy the items into the input array. For example, let's forget about recursion for a second. Imagine we have split this array into half, and now we want to combine these pieces. We can simply copy these items into the input array. There is no need to allocate a separate array, okay? So merge sort takes O of n space. Now, there are variations of this algorithm that can sort an array in place without requiring additional space. That goes beyond the scope of this course, and if you're interested, you can learn about it on your own. Just search for in-place merge sort. Now, spend 20 minutes and implement merge sort on your own. Then come back, see my solution.